Hey everyone. In the world of 3D math, there's one thing that is equally scary as it is fascinating.
Do you know what I'm talking about?
The Matrix.
Do you want to know what it is?
I'm sorry, this kind of joke will happen a couple of times. I will not resist my urge to do this. So, what is a matrix? It's actually relatively simple. It's basically a lattice deformer. So a matrix you can imagine as a box, or if you will, just three lines that define basically a box. And whatever you do with this box or those lines will also be applied in an indirect form, so to say, to the object that you apply the matrix to. So a matrix is nothing else really than a transform node, if you will, where you can change translate, rotate, scale, and shear to some kind of object, or maybe some points, or anything really. So it's just a transform really, including everything that we know from a transform node. To visualize this, I have an example here, and let's say we want to apply a matrix to our toy here. Now, the way you might have seen a matrix represented before is in this kind of, set of numbers. And this is, as you can tell, a 3x3 matrix, but there are also 4x4 matrices. But in 3x3, I think it's easier to understand because each of those rows here represent the direction of one line. So if you look at the first one here in front of us, that's the second line, and the direction it represents is 0, 1, 0, so upwards. The one at the bottom is 0, 0, 1, so into the Z direction. And the first one is X1 and then 0, 0, which represents this line. And this is how you would write a matrix. And as you can see, the toy actually just stands there as it would normally do, because this is a so-called identity, or you could call it a neutral matrix. And you can tell this from this 1, 0, 0, 0, 1, 0, 0, 0, 1 group here of numbers that represents an identity matrix. So let's change this setup so that you can see what it actually does. And what I did here is I built it so that these lines represent a matrix, which you can then see in the numbers, and this will deform the underlying toy. And if I just use a selection here, I can select, for example, this line and move it around. And you can see it changes the number of my matrix. So this would be how my matrix would look like. And you can see what I can do with this. By changing a bit like a lattice, this curve, I just change the underlying geometry. What I could also do is I take the whole thing, and with a transform node, I just rotate the whole matrix. And surprise, when I rotate the matrix, I also rotate the underlying object. So this is what we would call a matrix rotation. And likewise, if I, of course, scale my three vectors down, I do a matrix scale. And of course, what I could also do is a translation. For technical reasons, that doesn't work here, partly because this is a 3x3 matrix, and that doesn't include translation actually. But usually translation is not a big deal. So this is something we will not concentrate on anyway. But of course, we will see how it works. The most important thing really about a matrix is actually rotation. So it's basically a lattice deformer defined by three vectors. And if I change those vectors in any way I want, maybe I deform them in a surreal way, maybe something like this, you can actually see that the underlying geometry will be deformed in the exact same way. And the resulting matrix would look like something like this with those numbers. Okay, but don't worry, we don't actually have to set those numbers. I just want to explain what each of those numbers represent. Each line, each row represents one vector that together build the matrix.
What is the matrix? Control.
So what can we do with this? Well, first of all, let's actually look how we do this. And that is by changing this toy here with a matrix. So we create a point wrangle, because what the matrix is actually doing is it changes not the whole object, of course, but every element of it. And this we can use actually to our advantage later on. But for now, let's try to, translate, scale, and rotate this object via a matrix. The first thing we need for that is a matrix. And this matrix we create as an identity matrix. So that this works like this. We create a variable that is a matrix, and then we fill it with an ident matrix. And remember, this looked like this. And those numbers are basically now saved in this matrix M, and they represent a neutral matrix that basically does nothing. It's just a neutral box, so to say. Now, what we can do now is we can translate, and when you open the function translate, you can see this uses a matrix and then some amount to translate something. We can also scale with a scale command, which also uses a matrix, and we can rotate. And all those commands you might have seen before, and we're disappointed that you need a matrix for that, because those three standard, functions to translate, scale, or rotate in any 3D program on this planet are internally using matrices. So this is why those standard functions always need a matrix to work. So let's start, I think, with scale, because it's relatively easy to understand and see as well. And the interesting thing here is that the scale uses a so-called pointer. So the matrix here that we put in will directly change. And you can tell this from this little symbol here, this end symbol. And of course, we can also go into the help to see this again, maybe a bit bigger. This here represents, look, when you put in a matrix here, I will change this matrix. It will not give back a new matrix or anything, because the resulting data type is void, which means it doesn't give anything back. And then you have a scale vector, which simply represents the scaling of X, Y, and Z. So as you can imagine, probably the way you run this is this. You use the M that we just created, the box, the neutral box, and we want to scale it. And a neutral scale, of course, would be 1, 1, 1, because then we just multiply it by 1. And for this to now work, and this is interesting, there's no command apply matrix or something, but you just take the position of each point and multiply it with this matrix. And this is the moment where we basically apply our deformer, we apply our box or our lattice deformer, however you want to call it. This is called matrix multiplication. And as you can see here, those are the basic 3 steps we do. We create first a neutral matrix, we do something with that matrix, and then we apply this matrix to our geometry. Currently, nothing is happening. Why? Because we set the scale to 1, 1, 1. So let's change this. Let's scale it up by 2 in the Y direction. And there you have it. Now our toy is 2 times taller than before. We can also put 0.2 to this, and so on and so forth. So you get the idea. And of course, if we want to scale the whole thing by the same amount, then we can do this as well. And now we have a small toy. So relatively simple, as you can see, and not as scary as it seems. The same is true with a translate. So if we translate our matrix first, not the object directly, but the matrix that we then later apply, we can say, okay, move my object first by 0, 0, 0, because then nothing happens, so that we're back to normal. And then we say we move it into X by 1 meter. And who would have thought we actually now moved our toy 1 meter to X? So this, again, is relatively easy to understand, and this matrix multiplication only took us 3 lines. I just realized I probably should have scaled this up so it's easier to read. But the thing now is, none of this is really super interesting so far, because scale and translate are 2 things that are relatively easy to do without matrices. The main use case for matrices in my experience is always rotation, because believe it or not, for some reason, rotations in 3D are the most complex by far of the 3 transform operations. And this is why we will concentrate probably on rotate, because that's usually by far the most interesting concept. And the rotate works the same way though, only that we have now 3 inputs into our function here. The first thing, of course, is again a matrix. Then the amount we want to rotate, I don't know, let's put in 10. And I will already say it, this is in radians, not in degree. And then we define a vector that we want to rotate around. So if we want to rotate our object around the y-axis, we just set it to 0, 1, 0. And now the whole thing should rotate. By the way, it moved back because we turned off the translate. I should have done this step by step. But let's, instead of the 10, let's use maybe the current frame. What we can see now is that our object is rotating about around y, and it's pretty fast. And that is because, let's quickly change the light actually. And the reason it moves so quickly, or it rotates so quickly, even though we have real time turned on, is that this is not in degrees but in radians. So if you want to turn this into degrees, actually, the absurd thing you have to do is you actually turn this into radians, because that's what it expects. And that means what's inside of the radians function is actually then a degree. So we're converting what we want to a radian, and what we want is a degree. That's kind of the logic here. And as soon as we do this, then the current frame is not the radians, but actually degree, and you can see it's much slower. And usually that's what we do. We think in degrees, but we work with radians so that the rotate can work properly. And here you can see the idea. We can now rotate the matrix, for example, by the current frame around the y-axis, and then we just apply this matrix to each point of our geometry, and we have a matrix rotation. How is that different, or why is that helping us? Because we can do the same, of course, with a transform. And what's the big deal here? Well, a couple of things are not easily done with a transform. For example, if you have a box that you want to rotate, wherever, and you have a particular vector that you want to rotate it around, then you have a problem, because that's something the transform node is not able to do. But with a rotate matrix, what I can do now is I just read out this line, and actually let's do this from scratch. We start with the base setup. We first need a matrix M, which we initialize as an identity matrix that will do nothing to our box. Then we will do something to this matrix, rotate, we do this later, and then we apply this to each point by multiplying this matrix to our box. So what do we want to rotate, or how do we want to rotate it? Well, first of all, we can make sure that whatever we put in here should be in radians. Now let's put this onto a parameter that I already have created before called deg, for degree. And then that's the interesting thing here. How do we get this vector actually? Well, we have to calculate it ourselves, because what this vector is defined by is the first point and the second point, and between them is a direction. So what we do first at the very beginning, for example, is to read out the first point, and this will be we want to have the position of the first point, so let's call it P1. And with a point function, I can read out from the second input where my line is in the position of the first point. And we copy the whole thing because we're lazy, and do the same for the second point, which is now point number 1. And with those two, we can now calculate the actual direction, because it's simply, and let's already make sure that we normalize that, because that's always something you have to do. We just subtract one by the other. The order doesn't actually really matter in this case, but let's say we take 0.2 minus 0.1, and then we have a direction. And this direction we use as our rotation axis. And if we fill this down here with the current frame, or we just dial it in ourselves, we should be able to see, if we look through the result, let's dial it to 0. And let's show our line so that we can actually check if this worked. And the cool thing is the line can be anywhere. It now rotates around this line. It might not look like it first, but it actually does. And this is really cool, because now we can arbitrarily choose what we want to rotate around. And maybe we want to rotate this, which is probably simple. So let's choose something else, maybe this, I don't know. And then we can rotate around this axis relatively easily. Now you might think, wait a minute, for this there must be some kind of node, right? Well, to my knowledge, no. So if you look around, there is no rotate node. There is something similar, like it's called transform axes. There you can define a certain direction and then translate, rotate, and scale around that. But this direction you still have to, put in. So you could read this out somehow, sure, but you would still have to define it here as a vector. To my knowledge, there is no node that allows you to just put in a line and then rotate an object around it. This is something you would have to calculate yourself or build yourself. And we just did that with basically 3 lines that really do something, and the rest is really there just to calculate the direction. So overall, in 6 lines of Vex code, we built our own rotate around line function, or whatever you want to call it. And this is actually pretty cool. And again, as far as I know, there is no other way of doing this in Houdini. Now, this is cool and all, and now I can rotate stuff around a certain vector. That's cool. But actually, if you go one step further, you can do surprisingly crazy things with that. Because let's once again write this from scratch. And what we want to do with this weird shape here, let's first start by rotating it again around the y-axis. So what we need is a matrix. We start with a neutral matrix. We rotate this matrix around a radiant that we can control via a parameter. And then we want to rotate around the axis along y. And something went wrong. Let me check. Oh, ident. Sorry, it's not identity, but it's ident. Fair enough. And then we apply this to the position of each point by saying we multiply this with a matrix. And if I now create my degree controller, you can see a little bit of a movement here because I can only put the controller to 1 degree. So let's quickly change this in our interface so that I can actually rotate to 360 degrees. And you can see now we basically had what we've seen before. We can rotate around the y-axis. Now, what is cool now is that I can actually change this so that each point is actually rotated in a different way. For example, the higher we go, the more rotation. So it's very quite simple here. We can just multiply this whole thing. And the question is if you do it outside or inside, both will work. I think inside makes more sense. So I multiply the degree by the current height of the point. And what then happens is this. You get a different rotation for every point based on how high he is. And what we just built is our own bend deformer. And I think now you might start to understand why matrix multiplication is so cool. This just took us a single point wrangle with 3 lines of code to build a bend deformer. And this is actually what internally happens with a bend deformer as well. Instead of rotating every point the same way, it makes a difference where the point is in space, for example, along the height. Now we can actually combine this even with our line if you want. And then you have even more the concept of a bend deformer. Let's just steal our line code here. So the first 3 lines should just read out the direction. And let's replace this here in the back. And all we need now is an actual line and the second input that we can use. And now we can use this line and rotate around and do very interesting stuff with this, because now the rotation will happen relative to this axis. And here you can see what's happening. And once you've rotated it, of course, you can change this. And you might have seen this behavior in Maya before. Maya works in a similar way, where you can define an axis that you want to rotate around. So all kinds of crazy stuff is possible all of a sudden with the power of matrices. And with this, by the way, you can also create not the twist part of a bend deformer. Actually was not completely specific here. This here is a twist. And this also is a twist around a line. But if you really want to bend, you might have already an idea what to do. You just set the vector to be, in our case, Z. I know you can't see it because my head is in the way. But if you do it carefully, here you can see, since my axis basically is running like this now, you can also basically a bend deformer is a twist deformer at the same time. So let's change, for example, our degree parameter so that we can also do negative numbers. And then you can see that we can actually bend it now around this axis. And what you can see is it always rotates around the center of the world. And this is a very important concept that we have to talk about next. In this case, we can fix this easily by, for example, just making sure that our box here, whatever this is lying on the ground, and then our bending will actually work relative to the center of the world. But now we know that there is potentially a problem, and that is if we want to rotate something or deform something that is not in the center of the world, we will run into problems. And this is something we have to talk about next. Because let's say we have a rock here, a low-res rock, and we want to rotate it around itself in Y by using this code, because it's in the center of the world that we've seen before the code. That's easy to do. But what if this rock is somewhere else, like up there? Now we have a problem, because if we now try to rotate this, it still works, but it always rotates around the center of the world, not around itself. How do we solve this? Now this is a bit weird because we cannot actually change the reference point it rotates around. It will always rotate around the center of the world. So what you have to do is, before you apply the matrix, you actually move this object back to the center. Now, how do you do this? Well, you cannot just set the position to 0, 0, 0, even though that might seem instinctively correct. But what you then would do is you just set each point to 0. So that's not the way you do it. What you need to do is you need to calculate first the center of the object. And I think, as far as I know, we've seen how to do this before. So let's do this with a vector center, and we want to save it there. We use the get bounding box, and one of the get bounding box functions is get bounding box center. And this is really easy to do because you just give it a 0 for the current geometry, and that's it. And now in this variable center is the literal center of this object, which is cool because now the funny thing is we just subtract this center from the current position of each point. And this means, if you think about it a little bit, this is everything moves back to the center. Now you apply your rotation. Here it is. And now what you do is you move it back to where it was before by just adding the center position again. Whoop. And believe it or not, if you run this all together, you can see that now I can actually rotate my rock here around itself no matter where it is, because before I apply my matrix, I move it back into the to the center. You could also say technically that you move it back to the local space, because then each point is there where it would be relative to the whole object. So this is technically what you're doing here. You're moving the object from the world space to the local space, then you rotate it, and then you move it back into the world space. But if you just remember those steps, this will always work no matter what. Now, this is cool, but what do you do when you have multiple objects like this? I have a couple of rocks here that are, floating around in space. And if I try to copy my code, what happens is that it calculates the center of all the rocks and rotates around that, which is again not what we want. It seems to look like it's the center of the world, but it's not. It's actually the center of the whole group. So what you have to do here, as we've seen before, you actually have to use a for each loop where you do all this separately for each rock. And then you can actually do this for each rock separately. Of course, this is relatively easy to do otherwise, because you could do this also with a transform and and CEX and CEY, CEZ in the pivot. But there are certain things you can do with this. For example, you can change the rotation axis to not using the same for each rock, but you just use the curl noise, for example, and this time you wouldn't use the position probably, because then you would get a different result for each point, which you don't want. But you want to do something that is the same for each point of your rock, and that is the center, which is of course also a position in space. So by using a curl noise here, each rock will get a different direction that it will rotate around based on its center in the world. And then what you just created is a random rotation. Oh, something went wrong. A random rotation around each object. And what here happened is something you always have to keep in mind. The one thing I always put everywhere, and I will put it here again, is always remember to normalize. Normalize everything. Otherwise, you will get some unexpected results. So where at this point do I have to normalize? Actually, funnily enough, the curl noise. Because the curl noise, for some reason, doesn't always give you normalized directions. So let's make sure that the axis that we rotate around, which so far always was normalized, is normalized. And now if you try this again, you can see it actually works. And this is pretty cool, because now I can rotate each rock randomly in any direction with just one setup here at least. Okay, so that was a pretty long video about matrix multiplication. It's basically a transform saved in a data structure, and you can use that to translate, rotate, and scale basically anything, including applying those transforms differently based on the position of a point in space. And then you can create this kind of stuff and all kinds of other things you can do with this. Mostly use it for rotation, because that's the most complex stuff. It's a bit tricky to learn, but once it's in your arsenal of tools, of course, it's pretty powerful. So I really hope this was helpful. Thanks very much, and see you later. Cheers.